If you're a Square-1 solver, you might be familiar with the method known as CSP, or Cube Shape Parity. If you don't already know, one of the most frustrating things any beginner to intermediate Square-1 solver will have to face is parity, which requires a really long algorithm that can easily ruin your solves. Unlike big cube events, which also have long parity algorithms, the time it takes to solve a Square-1 is quite short, relatively speaking. This means that parity can make your Square-1 solves wildly inconsistent, with a huge time gap between solves that have parity and those that do not. The CSP method aims to fix this. The fundamental idea behind CSP is that you do a series of tracing steps during inspection to try to determine if you're going to get parity later in the solve. And if so, you try to fix the parity while solving cube shape, which is going to be much quicker than waiting to do the long parity algorithm at the end of the solve. But if you know anything about CSP, you'll know that the steps required to figure out if you'll get parity or not are very specific. This video isn't necessarily intended to be a tutorial for CSP, but just as a very brief overview, you first look at the colors of the first 3 black edges and determine whether they add to the parity count or not. Then do the same for the white edges, the black corners, and the white corners. Finally, you look at the pattern of every other top or bottom color for the edges and the corners, and add those to the parity count. Based off of all of this, you'll either end up with an even or an odd parity, from which you can determine how you need to solve the cube shape, such that you won't end up with parity later in the solve. But don't all these steps all feel quite arbitrary? I mean, why do these steps specifically tell you whether you'll get parity or not? This question is exactly what this video will answer. But in order to do that, we have to take a look at how this method was developed in the first place. First of all, let's define what we even mean by parity. Parity occurs when you have an odd number of swaps that need to occur between edges. For example, in this state, the cube has parity because it will take 1 swap to get to the solved position. This, however, does not have parity because it will take 2 swaps to get to the solved position. The exact same can be said about corners. This has parity and will require a long, annoying algorithm to solve, whereas this one will not. Armed with this knowledge, Matthew Sheeran created the first version of CSP around 2014. However, it's not quite like the version that's used today. The method he developed to consistently avoid parity used principles quite similar to that in blindfolded solving, where you can track cycles of where pieces need to go. Let's do a quick example. Starting at this black-blue edge, we can track that it needs to go here. The white-orange edge needs to go down here. The white-red edge needs to go here. And we'll continue this process until all of the edges have been solved. So far, we have 5 swaps, which is odd. Like I said before, however, parity also occurs when 2 corners are swapped. So we have to repeat the process for corners. Starting at the black-orange-blue corner, we track that it needs to go here, which goes here, which goes here, which goes here, which goes back to our original starting location, so we'll have to start a new cycle. I'll pick this black-green-orange corner, which goes here, which will just come back straight away. The corners had 5 total swaps, which is also odd. When you consider that both our edge and corner parity was odd, they cancel each other out, meaning our total parity was even. Sure enough, when we solve the cube normally, we don't end up having to do the pesky parity algorithm. This method works great when the cube is already in cube shape, but it gets tricky when you're dealing with other cube shapes. Let's take this scramble, for example. Let's start with the white-orange edge, which will go, well, where does it go? It's not really obvious where it should go, is it? When we had it in Square, it was easy. We just used the solved state as a reference, and then tracked where all of the pieces should go according to that reference. But now that we have a different cube shape, there's not really a reference that we can compare it to. The way we get around this is just by making our own reference. Technically, any scramble that has a cube shape of scallop could be used as a reference, but having a simple reference scheme, such as this one, makes it much easier to memorize. So now, starting at this white-orange edge, we know it needs to go here, and the white-green edge needs to go here, and the black-green edge needs to go here. and you'd continue doing this for the rest of the edges and the corners until you've reached either a total, even, or odd parity. It's also important to memorize how you're going to solve each case based on the parity you get. For scallop, if you trace an even parity, you're going to solve it as normal. But if you trace an odd parity, you're going to add an extra slice and then solve as normal. Going back to our scramble, we traced a cumulative odd parity, so we're going to solve accordingly. And sure enough, we've successfully avoided encountering parity at the end of the solve. This method was certainly a huge step towards making Square-1 times faster and more consistent. In fact, according to Ro Hessler, who was supposedly the first person to fully memorize CSP, it's easily taken 1 to 1.5 seconds off of my average in only 1 month of using it. However, there were certainly some drawbacks. For one, you'd technically have to memorize a different reference scheme for all 90 cube-shaped configurations. Although this is certainly alleviated quite a bit by trying to maintain a consistent order of colors, it's still not perfect. Secondly, this method is slow. Attempting to track cycles of pieces while simultaneously trying to recall the specific reference scheme for that case takes a lot of time and effort. Not to mention, doing all of this within the 15-second time limit for inspection is, although doable, quite unrealistic for most solvers. If there were only some way to track the parity of the scramble without using a reference scheme, all of these problems would be solved. This is exactly what Cale Schoen set out to discover, and the method that he came up with was frankly revolutionary. So, what exactly did he do? To explain his method, it'll actually be easiest to step away from the cube and use playing cards instead. We have 8 cards here that represent the 8 edges on the cube. 4 of them are black to represent the black edges, and 4 of them are red to represent the white edges. This configuration will represent our solved state. So now, let me ask you this. If I were to shuffle all of these cards, how would you determine how many swaps it would take to get back to the solved state without tracking cycles of cards? Well, that's kind of a hard question to answer, so let's simplify it a bit by completely getting rid of the red cards and focusing just on the black cards. If we swap the first and second cards, we know that we are only 1 swap away from the solved state, meaning that when the cards go in the order 2, 1, 3, 4, it has an odd parity. But since there are only 4 cards, we don't even need to know the last card, because it will always just be whatever card doesn't appear in the first 3 cards. So we can modify our statement from before to say that whenever the first 3 cards go in the order 2, 1, 3, the configuration has an odd parity. However, we can swap the 3 and the 4, and now we're only 2 swaps away from the solved state. So whenever the first 3 cards go in the order 2, 1, 4, the configuration has an even parity. The key thing to realize is that when we changed the last of the 3 digits, the parity also changed. Now, let's go back to the solved state and try this again, but let's swap 1 and 3. Now we know that the order 3, 2, 1 has an odd parity, but 3, 2, 4 has an even parity. We can repeat this process where we fix the first 2 numbers and then record the parity of the 2 remaining possibilities for the third number. If we do this for every possible configuration of 4 cards, we'll end up with a list of 24, or 4 factorial configurations for the first 3 cards, 12 of which have an odd parity, the other 12 of which have an even parity. So now, if we were to shuffle the cards randomly, we could just look at the first 3 cards and reference the list to see if it has an odd or even parity. It may seem like there's a better way of doing this, which, don't get me wrong, in the context of cards is certainly true. But this method is not only the fastest with enough practice, but it also translates the best to the Square-1, where we're working with colors and not numbers. Now we have a way of figuring out the parity of the black cards. When we bring back the red cards, we'll of course have to repeat the same process on the red cards. So combining the parity of the order of the black cards and the parity of the order of the red cards should be all that we need, right? Well, not quite. If we were to swap the black 4 and the red 1, for instance, the order of both the black and the red cards is maintained. This means that the parity of the order of both the black and red cards is even, We can even reference the list to make sure. As such, the total parity should also be even. Yet, this obviously isn't true since we're one swap away from the solved state. So there must be another variable we have to keep track of to determine the parity. Our problem before came from the fact that we treated the black and red cards separately, but we never considered what would happen when the black and red cards interact. Well, if we swap a black card and a red card like we did before, you'll notice that a red card now comes before a black card. This never happened in the solved state. However, if we swap another pair of a red and a black card, so we'll now have an even number of swaps, we'll have two red cards coming before a black card. Based off these results, let's for now assume that when a red card comes before a black card, which we'll call a black-red inversion, it will add to our total parity count. We can see that this holds true even if we swap the black 3 and the red 1, for example. The red 1 comes before two black cards, so it maintains an even parity. However, we messed up the order of the black cards. Its first three cards are now 1, 2, and 4, which, if we reference our list, we'll recognize is odd, meaning our total parity is odd. This makes sense, since we did one swap to get here. As it turns out, our assumption about inversions that I just mentioned shortly before is 100% true. This is because if we make a swap, like the black 4 and the red 1, where the combined parity of the order of the black and red cards is maintained, you are guaranteed to have an odd parity for the black-red inversions. Though, as we just saw, it is possible to make an odd number of swaps and have the black-red inversion parity still be even. However, this will always mean that either the parity of the order of the black cards or the red cards has changed. So, on one hand, we're done. We've successfully found a way to track the parity of these 8 cards without tracking cycles, and thereby avoiding the necessity of a reference scheme. I mean, you can even try it yourself if you want. Shuffle the cards, then combine the parity of these 3 variables we just discussed, and it will tell you the overall parity of the configuration. However, if you're familiar with CSP, you'll know that the method we use to track the parity of the black-red inversions doesn't seem to correspond with anything we actually do on the Square-1. This is because there's actually a much faster method of tracking this specific parity. To derive this method, let's first try to find some mathematical expression that can represent the black-red inversions. To start, let's number the position of all of these cards from 1 to 8, starting at the top left card, going down the row, and then moving on to the next row. Then let's define some variable bk, such that bk is 1 if the card at position k is black, and 0 if the card at position k is red. For example, in this configuration, this means that b3 is 1, but b5 is 0. Let's also define two integers I and j, which are just going to represent different card positions, so they can be any number from 1 to 8. However, we're going to say that I always has to be greater than j, no matter what. We can represent whether two cards at position I and j are a black-red inversion with this expression. Why does this work? Well, let's look at the first part, bi. Like I just described, if the card at position I is black, it will evaluate to 1, and if it's red, bi will evaluate to 0. Next, let's look at 1 minus bj. If bj is 1, meaning that the card at position j is black, this term will evaluate to 0. If bj is 0, however, meaning that the card at position j is red, it will evaluate to 1. So, what this means is, when we multiply these two terms, the product will be 1 if and only if the card at position j is red and the card at position I is black. In any other scenario, at least one of these terms will be 0, meaning that the product will also be 0. Since I always has to be greater than j, this means that if the product is 1, it must represent a black-red inversion, in which a red card comes before a black card. So now we've successfully created an expression that will evaluate to 1 if the cards at position I and j represent a black-red inversion, and 0 otherwise. Thus, to count all of the black-red inversions out of the 8 cards, we can sum up the number of times this expression evaluates to 1. this sum can be represented like this. All this is doing is going through every allowed combination of I and j based on our restrictions from before, and adding 1 to the sum if I and j satisfy this expression as a black-red inversion. Let's now do some rearranging. We can distribute the bi, then split it into two separate sums. But for now, let's focus just on this second term and see what it's actually doing. Similarly to before, when we built this expression to represent a black-red inversion, this expression simply represents a black-black pair. This is because if either of these terms is 0, meaning that the card at its position is red, the product will also be 0. Thus, this product will only be 1 if the cards at positions I and j are both black. So really, this sum is just counting the possible black-black pairs out of the 8 cards. But since this sum only considers black cards, we can just calculate it because the configuration of the 8 cards has no effect on the number of black-black pairs. It can be calculated by doing 4 choose 2, because we are looking for the number of ways to choose 2 black cards out of the 4 total black cards. 4 choose 2 turns out to just be 6, but we're only concerned with the parity of this entire expression. In other words, we don't actually care about the number of black-red inversions. We just want to know if that number is even or odd. As such, we can just reduce this entire expression by mod 2. Since 6 mod 2 is just 0, the 6 disappears and we're left with this double sum. What's important to note here is that this term, bi, doesn't depend on j at all. So now we're going to try to rewrite the entire sum so that it only depends on I. To start, let's expand the sum to see what it's actually doing. Let's condense this a bit. As we can see, b2 gets repeated once, b3 gets repeated twice, and this repeats all the way up until b8, which gets repeated 7 times. So really, this can just be condensed even further into the sum of bi times I minus 1, as I goes from 1 to 8. And just like that, we've successfully removed j from our expression. Now let's think about which values of I actually contribute to the sum. One could observe that if I were odd, that would necessarily imply that I minus 1 must be even. An even number multiplied by an integer is still even, because it will always be divisible by 2. However, like I mentioned before, we only care about the result of this expression mod 2. And thus, if the product of these two terms is even, that's the same as it being 0. This means that the only possible values of I that may contribute something to the sum are even values of I. So let's completely throw away any odd values of I in this sum. Now that we know the only values of I in this sum are even, that must mean that I minus 1 is odd. But mod 2, that would just evaluate to 1. This means that our final sum to count the parity of black-red inversions is the sum as I goes from 1 to 8, but only the even values in that range of bi. Expanded out, this is just b2 plus b4 plus b6 plus b8. So, if we transition back to the cards, this would mean going through the cards in the even index positions and adding 1 to the parity if the card at that index is black. And this is it. As you can imagine, this method is far quicker than what we were doing before, with manually counting the number of times a red card came before a black card. Just like that, we've officially constructed a fast, easy way to count the total parity of 8 cards. And as you may have already guessed, these methods also apply to the Square-1, regardless of its cube shape. We only used 8 cards, even though there are 16 pieces on the Square-1, but that's because the process for tracing the edges and corners is the exact same. So we'll just have to repeat this process for both edges and corners, for a total of 6 variables that can affect our total parity. The methods I just used on the cards transition pretty seamlessly to the Square-1, with only a couple minor nuances. For one, the Square-1 obviously has colors, not numbers. So we can just assign a color to each number, and then replace each number with its respective color on our list. From here, we can just memorize all 24 possible combinations to know which ones correspond to a parity and which ones don't. This may seem like a lot, but there are strategies to make it easier, and it becomes pretty automatic once you have enough practice. If you know CSP, you may have already realized that we don't actually count the number of black pieces in every even position. We do it for every odd position. But these two things actually do the exact same thing. I mean, if you think about it, you'll realize that since there are only 4 black edges or corners, if there are an odd number of pieces in the even positions, that necessarily implies that there are also an odd number of pieces in the odd positions. Same goes for if there's an even parity. And this is still the method that is used today. Now, instead of memorizing a reference for each case, you just have to memorize a solution for each cube shape based on if the parity is even or odd. Don't get me wrong, it's still a lot to remember, but it's much easier than what it was in the past. CSP went from being a method that only the top Square-1 solvers had enough will and dedication to utilize, to being a method fairly accessible to anyone with enough determination to make their times faster and more consistent. If you don't already know CSP and would like to learn it, I'll link a couple resources in the description to help you out. But with that being said, thank you very much for watching.